Welcome back. Previously, we explored the fundamentals of motion, tracking an object's travel through the lenses of uniform and non-uniform speed. However, speed is limited to measuring magnitude. It contains no information about where an object is actually heading. Imagine you are on a fishing boat when a radio alert warns of a violent storm nearby, with wind speeds of 100 kilometers per hour. That 100 kilometer per hour figure is useless unless you know the storm's heading relative to your coordinates. In this scenario, direction is a matter of survival. Measurements that only describe a raw amount or magnitude are called scalar quantities. This includes your mass, the area of a room, or the length of your boat. We use scalars for simple metrics like the speed shown on a dashboard, which tells us how fast we are moving, but nothing about where we are going. Vector quantities require both a magnitude and a specific spatial direction. Adding this directional arrow to the speed reading transforms the data into a vector, pinpointing exactly where the storm is heading. To accurately predict how the universe moves, we must add this arrow of direction to our measurements. We see the difference between scalar and vector data clearly when comparing distance and displacement. Distance is the total length of the actual path you cover. It is a scalar quantity that tracks the total effort of travel while ignoring direction. Displacement is a vector. It is the shortest possible straight line from your starting point to your final position in a particular direction. Consider a specific path. You walk 4 meters east, 3 meters south, 4 meters west, and 3 meters north. Because vectors rely on direction, opposite movements cancel out. The distance you traveled east is negated by the walk back west. In this loop, you've traveled a distance of 14 meters, but because your directional movements balanced out, your displacement is 0. Direction dictates the physical outcome. An object can travel a massive distance and still end up with 0 change in its position. This leads us to velocity, which is defined as displacement over time. Velocity is speed with a direction. While speed describes a truck moving at 40 kilometers per hour, velocity specifies that the truck is moving 40 kilometers per hour north. A body is in uniform motion if it covers equal distances in equal time intervals while maintaining one specific direction. Non-uniform motion occurs when an object speeds up, slows down, or shifts its physical direction. Consider a toy train moving at a constant speed along a circular track. Even though the speed never changes, is the train accelerating? It is. Acceleration is the rate of change of velocity. Because velocity is a vector, any change in direction counts as a change in velocity. As the train follows the curve, its physical direction shifts. Mathematically, turning a steering wheel causes just as much acceleration as stepping on the gas pedal. Because velocity relies on direction, any shift in heading guarantees a state of acceleration. These directional changes and accelerations are caused by a net force. Without an unbalanced force, an object's velocity remains constant. If you push a book across a table, the invisible force of friction acts against that motion. This creates a negative acceleration until the book halts. Newton's second law shows that acceleration is directly proportional to the net force and inversely proportional to the mass. To maintain constant velocity, your applied force must perfectly balance opposing forces like friction. When the net force is 0, the object avoids acceleration and maintains its state of motion. These same principles apply vertically. When an object is dropped, the force of gravity pulls it toward the Earth's center. This force causes a falling object's velocity to increase every second. We represent this constant downward acceleration as g, roughly 10 meters per second squared. A spring balance measures this gravitational pull. The extension of the internal spring is directly proportional to the force acting on the mass, which we record as weight in newtons. While mass measures the matter itself, weight is a situational vector that depends entirely on your location in the universe. Mass is the raw amount of matter contained within an object, a scalar value that remains constant regardless of where you go. Take a 60-kilogram astronaut standing on the surface of planet Earth. On Earth, gravity pulls on that 60-kilogram mass with a force of roughly 600 newtons. This is the astronaut's weight. If that astronaut travels into deep space, the environment changes, but their physical composition does not. Their body still contains 60 kilograms of matter. Their mass is unchanged, even though their weight has vanished, because there is no gravitational pull. On Jupiter, the gravitational environment is far more intense. Because Jupiter's massive gravity pulls harder on that same 60 kilograms of mass, the astronaut's weight increases by 2.5 times, rising to 1,500 newtons. Your mass is a universal constant, but your weight is a vector dictated by your surroundings. In a vacuum, gravity acts as a universal equalizer. While a heavier object experiences a stronger gravitational pull, its greater mass also provides more resistance to being moved. Because these two factors balance perfectly, all objects are accelerated at the same rate. If acceleration due to gravity acts on all objects equally, regardless of their mass, if you dropped a 100-pound iron ball and a light feather on the airless surface of the moon at the exact same time, which one would hit the lunar surface first? Think you know the answer? Drop your thoughts in the comments below. If you guessed right, you're already thinking like a modern physicist. If this video helped make physics crystal clear for you, hit that like button, share it with your classmates, and don't forget to subscribe and ring the notification bell so you never miss our next 3D science deep dive. Keep questioning, keep exploring, and I'll see you in the next video.